Hi everyone, this is lesson number 17. Lesson 17 covers two things. The first is we're going to finish up talking about equilibrium, and then we're going to move on to acids and bases. I say end of equilibrium, but it's not the last time. We'll be using ice diagrams for basically the rest of the quarter. But this is the last part of that chapter or section. Okay, this is posted on May 13th. So the rest of this week, Zoom will be office hours. We'll have homework number 14 and 15 will be due on sapling. Next week, we have Zoom office hours. The homework for this one will be due on Wednesday via sapling. Okay, that's Wednesday, 5/20. Office hours and SI, we're going to really hit hard equilibrium. Equilibrium's tough, so make sure you're trying to get all the help you can from us. Okay, so we have a little bit of a review. Last time we talked about ice tables, and we talked about some tough ones where we can't assume x is small. Just remember that we can assume x is small in two cases. One is that Q and K are both smaller than 0.01, or that they both are larger than 100. So if I look at these four, in the first one, Q is 0, K is 1.5 times 10 to the minus 5. That's smaller than 0.01, so I can shift. Number 2, Q is smaller than 0.01, but K is larger than that, so no, I can't. Number 3, Q is 0, K is really big, so no. And number 4, Q is infinity, that's greater than 100, and K is also greater than 100, so yes, I can. All right, one thing, notice how, hey, I'm only shifting from Q equals 0 to 1. Isn't that a small shift? But remember, Q and K are always products over reactants. So if I have a Q of 0, that means my products are equal to 0. Okay? Now, if K is equal to 1, what that means is that my products must equal reactants. So I'm going from a point where I have no product to a point where I have equal amount of product and reactant. That's a big shift. That's why we can't use the assumption. Okay, let's move on and let's talk. We're going to go back to chapter 16. Chapter 16 was the one on free energy and thermodynamics. And the last part of chapter 16.4 was relating free energy to equilibrium. Okay, so we're going to go over this. Now remember free energy. Free energy, or delta G, told me whether something was spontaneous or not. If delta G is less than 0, it's spontaneous. Greater than 0, non-spontaneous. We also just found out about Q. Q is the reaction quotient, and it tells us how far between all reactants and all products do we have. Okay. Now, it turns out that we can relate Q to delta G to this equation here, right? Delta G equals delta G naught. Remember that naught means standard conditions, plus RT times ln Q, right? We can use this to figure out delta G under non-standard state conditions. Okay? R is in 8.314 joules per mole K, and temperature is in Kelvin. All right, now let's just look at this equation and let's just talk about something. At equilibrium, delta G is equal to 0. Okay, I kind of glossed over that earlier, but delta G equals it's at equilibrium. Okay, so delta G is equal to 0, Q is equal to K. So if I plug these two things into it, I get 0 equals delta G naught plus RT ln K. I can rearrange this to get this equation here. What this equation tells me is if I know something about the equilibrium constant, I can use that to determine whether something is spontaneous. I can connect equilibrium to thermodynamics. This can be rearranged to get this equation right here. Okay, I'm just taking it, and the opposite of ln is E, so I do that. These are the same equation, just I have two different things, right? Which one do I use? I use whichever one I want. If I have K, I can plug it in here to get delta G. If I have delta G, I can plug it in here to get K. All right, let's do an example. Oops. Let's say we have this equation, AgCl going to form Ag plus Cl minus. And we want to know, so at equilibrium, we're given Ag plus and Cl minus. And we're asked what K is, and we're also asked what delta G is. All right, so let's put this on the board. AgCl solid goes to form Ag plus Cl minus. All right. Now, we don't have to do an ice chart because, remember, ice charts are in order to figure out equilibrium concentrations. But we're already given equilibrium concentrations, right? We're given that Ag plus is 1.3 times 10 to the minus 5. And this is also 1.3 times 10 to the minus 5. So if I want to find K, I can just use my equation for K. So K is going to be Ag plus times Cl minus. All right, so I can plug in those two values. And I will get my value for K. Figuring out K and figuring out equilibrium is a lot easier when it tells you the answer, right? Unfortunately, we haven't seen that all the time, right? All right, so this means that my K is going to be 1.7 times 10 to the minus 10. Okay? All right, so now that I have K, let's just understand what this means real quick. Right? K is 1.7 times 10 to the minus 10. This is a very small number, right? So what that means is when I put that silver chloride in there, I get very small amounts of this, right? And in fact, in 215, if we studied AgCl, this is one we said it was insoluble. In reality, just a tiny bit of it is soluble. We'll talk more about that in a couple weeks. All right, now that we have K, we can go ahead and we can figure out delta G naught. Okay, so we want to know delta G naught. Notice I have two equations there. Both have K, both have delta G naught. Which one am I going to use? Well, they're actually the same equation, so I'm going to use the form of it that makes my life easier. I'm going to form this because what? I know R, it's on the screen. I know T, it's given to me, 298K, and I just found K, so I can plug that in. All right, so this is going to be negative 8.314 joules per mole K times 298K times ln of 1.7 times 10 to the negative 10. All right, I first start off, I'll multiply those two together. 8.314 times 298. That's going to get me negative 2477.6 joules per mole. I now multiply that by the ln of 1.7 times 10 to the negative 10. That's going to get me negative 22.5. Be very careful with that negative sign. Make sure you remember it. Multiply that by that number. And I'm going to get 55,734 joules per mole. Or 55.7 kilojoules per mole. All right, so what does this mean about my reaction? If I have a positive delta G, that means it's going to be non-spontaneous. Okay? So what does this mean? What this means is I can have information on equilibrium and I can get thermodynamic data out of it. That's kind of cool, right? Not really, really cool, but just kind of cool, you know, if you're into chemistry. All right, so let's look at this on the screen. So first thing we do is we put in our values for K. Remember that AgCl is not in here. Why? Because it's solid. So we just put a 1 in its place. We find our K. It's really small. And then we plug that in and we can get our delta G. Okay. Notice that under these conditions, it'll be non-spontaneous. All right, so if I look at this value, the ln of K, okay, if I ever take the ln of 1, the ln of 1 is 0. All right, do it on your calculator, prove that to yourself. All right, so if I ever have ln of anything smaller than 1, let's just say, so K less than 1, it's going to get me a negative value. So then I'd have a negative value here times negative, so that will get me a positive delta G. Okay, it'll be non-spontaneous. If K is greater than 1, right, so if I take 3, do ln of it, I get 1.09. I get a positive number. That's going to give me a negative delta G. That means it's spontaneous, right? So based on my value for K, I can tell you if something is spontaneous or non-spontaneous. All right, so let's go ahead and do the reverse way. This is video problem 17A. In this problem, you're given you're given delta G, and you want to use that to figure out K. And then once you know the value of K, it asks for the concentrations of K plus and Cl. All right, so that is the end of that last section on free energy and equilibrium, right? We have these two equations, and we can relate them, use this to relate free energy and equilibrium. Now, I have here on the bottom, you can actually also add in all these other things, like delta H and delta S, right? If I knew delta G, I could then figure out my enthalpy, right? Etc. Okay? That's something more for the fun. Okay, so now let's move on. And now we're going to start chapter 14. Okay? Chapter 14 is all about acids and bases. So we've talked about mechanisms, we talked about equilibrium in this section. Now we're going to talk about acids and bases, and then later a little bit on precipitation. Okay? All right, so we learned about acids and bases in 215. We said that acids produce H+, bases produce OH-, also known as hydroxide. All right. And we know about acids and bases in everyday life. Coca-Cola has acid in it. It adds phosphoric acid. But if I had really strong acid and I take a bath in it, it's not going to, just bleach my skin. It's going to do worse things. Bases. Bases are things like soap or things like Clorox, right? We can either have strong or weak, okay? All right, so we have acids produce H+, bases produce OH-. Number one thing you need to know that. Okay, all right. So, last time, what we did, that definition, that acids produce H+, excuse me, this was proposed by a scientist called Svante Arrhenius. Svante Arrhenius said this, and that's why we call this Arrhenius acid. Okay? Now, in reality, we don't just have H+. In reality, that H+ bonds to an H2O and it forms H3O+. So I get HCl plus H2O liquid forming H3O plus Cl-. A lot of times in this class, we're just going to, for simplicity, say H+. But in reality, that's H3O+. Okay, a little something about naming. When we talk about acids, we can talk about hydrochloric acid, hydrobromic acid, hydroiodic acid, HCl, HBr, HI. We also have nitric acid and perchloric acid, sulfuric acid, and phosphoric acid. These are all common acids that you should know and be ready to use. In a little bit, we'll talk about weak versus strong acids. All right, bases. Bases they produce OH-, right? And we don't have necessarily special naming, right? For instance, NaOH is just sodium hydroxide. CaOH2 is calcium hydroxide. Bases are also known as antacids. Think of antacid as being anti-acids, right? If I have heartburn, that means that stomach acid's coming up from my stomach, right? And what do? I put in a base there to fight it, okay? That was the simple definition. It was by Svante Arrhenius. Acids produce H+, bases produce OH-. It's too simple. We're going to actually make it more complicated, and we're going to talk about something called Bronsted-Lowry definition. Bronsted-Lowry is a definition of acids and bases by two scientists, Johannes Bronsted and Thomas Lowry. And it's more it's a better definition, but we should remember these ones here, right? Because we should know acids H+, bases OH-. Okay. All right. So what is the Bronsted-Lowry definition of acids and bases? Well, they said that an acid is a compound that donates H+ to another compound. By the way, H+ is a proton, right? Because hydrogen has one proton and one electron. So if I take away the electron, now I'm left with H+. Bases, they said, are compounds that accept a proton or an H+. Okay? So it's kind of like yin and yang, right? Instead of saying that bases produce OH-, they're saying they just accept H+. Okay? Notice that the definition for acid between the two are very similar. Okay? Next chapter, we're going to actually go on and we're going to talk about a more general definition. This is called Lewis acid and bases. But this is for very unique circumstances. All right, but let's look at Bronsted-Lowry and acids and bases. Okay. So let's say we have this reaction. HCl plus H2O goes to form H3O plus and Cl minus. We can look at this equation. Notice it is reversible. And we can look at this and we can say what's an acid and what's a base. Okay? Look at the HCl. What does HCl do? It loses an H+ to become Cl minus. So that means that HCl is an acid. What does the H2O do? The H2O actually gains an H+ to become H3O+. That means that my H2O here, my H2O is a base. Okay. All right, notice that in the simple definition by Svante Arrhenius, we wouldn't have called H2O a base here. We would have just said add something, right? Because it's not producing OH-, right? So H2O is a base. HCl would have been an acid in either definition. All right, now let's go ahead and let's reverse this reaction. If I had the reverse reactant, H3O plus Cl minus going to HCl and H2O. If I notice what the H3O does, plus, it loses an H plus to become H2O. That means it's an acid. Cl minus actually gains an H plus, and that means it's a base. Okay, bases accept, acids donate. All right, let's look at these two reactions, right? The forward and the back. Notice how my HCl, which was an acid, produced something that was a base. And my H2O that was a base produced something that's an acid. Okay? These two things are linked. And we actually call them conjugates. Okay? So a acid, like HCl, is going to lose an H plus to become a conjugate base. Okay? Notice I say acid goes to form H plus conjugate base. Bases, such as H2O, gain an H plus, right, to become conjugate acids. So acids become bases, bases become acids. We always call the conjugates the ones on the product side. Okay? All right. Now, acids and bases are always linked. Okay? If something loses an H plus, something else has to gain it, right? So I can't have a reaction with just an acid and no base. I need to have an acid and a base, kind of like redox reactions. The order doesn't matter, right? I can put acid plus base, or I could put base plus acid. A lot of times what we do is we have some abbreviations. Acids we can abbreviate as HA, A being for acid, H being the fact that it has a hydrogen. And what happens when it loses that HA? It becomes A minus. Okay. We call bases B, and what does a base do? It gains an H plus to become HB plus. Okay. All right, so let's go ahead and let's look at some reactions, and let's determine what our acid, base, conjugate acid, and conjugate base are. Okay. Notice I put an acid plus base. It doesn't necessarily have to be in this order, right? Okay, so let's go ahead and do this on the board. I wasn't planning to, but I think it'll help. All right, so we have NH3 plus H2O going to form NH4 plus OH minus. All right, what I want to do is I want to look at each one of these in turn, and I want to say, hey, what's this doing? So NH3. NH3 either gains or loses an H plus. Well, it's not connected to OH minus, it's connected to NH4 plus. So what's it doing to get from NH3 to NH4 plus? It's gaining H plus. So if it gains an H plus, that means that this must be my base. All right. If that's the base, that means the H2O should be an acid. Let's make sure that makes sense. H2O to OH minus, it's losing H plus. That means it must be an acid. Now, if that's the case, that means the base must produce a conjugate acid, and the acid must produce the conjugate base. Okay? My conjugates, I always say, are on the product side. Now let's go ahead and let's just reverse this. Let's say I had NH4 plus OH minus going to form NH3 plus H2O. In this case, my NH4 plus loses an H plus, so that means it must be an acid, and it forms a conjugate base. My OH minus gains an H plus, right? So that means it must be a base, and this must be a conjugate acid. Notice my NH3 is a base here, conjugate base here. It's an acid here, conjugate acid. Conjugate acid, acid, conjugate base, base, right? The same thing's happening, just the direction, right? And so conjugates are always on the product side. All right, so there they are on the screen, right? We always go ahead and we make sure to know what's happening. And there's always acids and bases connected. Okay, let's go ahead and have you guys do video problem 17b, right? In the first three, you need to identify the acid, base, conjugate acid, and conjugate base. In 4 and 5, I ask a question. I say HF is an acid, so what does it produce? And I say Na3 minus is a base, so what is its conjugate acid? Okay? You should know those definitions by heart. Acids donate H plus, bases gain H plus or accept H plus. Okay? Acids lose H plus, bases gain H plus. All right. Now let's go ahead and let's look at these equilibrium equations a little bit better. All right, so we can look at an acid. So an acid such as HBr. HBr is going to lose an H plus to become Br minus. We can write this in either two ways. We can have it reacting with water to form H3O plus, or we can just write it saying it loses that H plus. Now in reality, we know that this is H2O. There's also H2O here. This is called acid ionization. Okay? Acid ionization is the reaction of an acid and water. Now, because these are reversible reactions, that means they have K's associated. And we call it Ka to stand for the fact that it's acid dissociation. So I do products over reactant. H3O plus times Br minus over HBr. Notice the H2O is not in there. Why? Because H2O is a liquid. Or H plus times Br minus over HBr. Okay, this is my my equation for Ka, for acid dissociation. Okay? Now, the bigger Ka is, remember that, I wrote a very big K, I guess. It's products over reactants. Okay? So the bigger Ka is, the more products I get. That's what we call a strong acid. It dissociates almost completely to form products. It has a large Ka. A weak acid is one with a very small Ka. And it dissociates, it forms H plus only a very little bit. Okay? So we have strong acids and weak acids based on their Ka. All right. In the same way that we talked about Ka and acids, we can also talk about bases. Bases, such as NH3, they gain an H plus from water, and they form NH4 plus and OH minus. This is called base ionization, the reaction of a base and water. All right. Now, in base ionization, We can then write a K. We'd have NH4 plus times OH minus over NH3. And this we call KB. B standing for base. The stronger the base, the larger KB is. The more OH minus you pour. The weaker the base, the smaller the KB. Next time, we're going to talk all about these things and what it means to have KAs and KBs. Actually, we'll do that in 2 lessons. Our next one is on pH. Okay? All right, now, we've gone through some problems. We've had some things. We've called them acids, bases. Some of these are actually from the video lesson you're going to do. And what you should know is that some compounds are always either an acid or a base. OH minus, right, like in this equation, it's always going to be a base. HBr is always going to be an acid. But some things are sometimes an acid and sometimes a base. Okay? Notice in this equation here, the H2O loses an H plus to become OH minus. That means it's an acid. And in this one, my H2O actually gains an acid, H plus, so that makes it a base, right? So this thing about water, the fact that it can be an acid or a base, is going to be very important, and that's what we're going to talk about next time. All right, so that is it for lesson 17. We started off talking about a little bit about equilibrium. Now acids and bases. Get these down. If you get to the test and you have to remember, oh wait, do acids donate or accept? It's going to take too long, right? So acids produce H plus, bases accept H plus. Acids plus water form H plus conjugate base. Bases form a conjugate acid by stealing an H plus from OH minus. That's what we call Ka and Kb. All right, so that is it for lesson 17. Remember, the homework for this is due Wednesday, May 20th via Sapling. There's not a lot else to report because we just had our test. So talk to you all later. Bye. Oh, one last thing I should say. This section, it's longer. Usually we only have 2 weeks worth of things in the test. This next one will be 3 weeks, so 9 lessons. So it's a little bit tougher. So make sure you get work on it now. Don't wait till the test. All right. Bye-bye.